Hi, this is Victoria Forsyth. Thank you very much for attending my poster at CEDAR 2021 workshop. Today we'll talk about the retrieval of the electron density profiles from the ionosonde virtual height data. Let me start with some mathematical formalism for this problem. So if we know the emission frequency of our ionosonde, then the ratio of the plasma frequency over the emission frequency squared would approach 1 when we move closer to the reflection height. On the other hand, the phase reflective index mu approaches 0 as we get closer to the reflection height. The virtual height is the integrated group refractive index mu. So for a particular ionosonde frequency of 3 megahertz, for this profile, I'm showing the group refractive index mu prime with the blue line. So you see that it's very close to 1 below the reflective height. And then when it reaches the reflection height, it increases really sharply. So integration step needs to be very small when we approach the reflection height. For this particular ionosonde frequency of 3 megahertz, the integrated blue line would give us this data point, which will be the virtual height recorded by the ionosonde at the frequency of 3 megahertz. And for the whole profile, if we change the ionosonde frequency, we can obtain this trace of the virtual height shown with yellow. So we need to establish the inversion of the virtual height to electron density profiles using assimilative formalism. In particular, we use the Kalman filter equation to do the work. One important component of this equation is this matrix H, which is observational operator, which converts a vertical column of electron density into just one virtual height point. This operator is nonlinear, mainly because the x is also not linear. It's a logarithm of electron density. So we need the Jacobian then to deal with this nonlinearity. And the Jacobian is the partial differential of the observational operator with respect to the background model, which is expressed in this equation. And this dh prime dx can be split into two portions. One is due to the direct modification of the density in the grid cell, and another one is due to the variation of the reflection height. Okay, let's look first at this first component. So the group refractive index, mu prime, is not constant inside of the one grid cell in the assimilation scheme. So let's say we have this one grid cell, the bottom height is 120 kilometers, the upper height of the cell is 126 kilometers. So as we showed here in this picture, the group refractive index is not constant and it can increase really, really sharply inside of one grid cell. The d mu prime dx is also not constant. Here I'm showing it with white bars. But also the change in one grid cell influences the change in the neighboring cell in this d mu prime dx. So in order to account for this change at the neighboring points, we introduce some height dependence to d mu prime dx. For example, these white bars would show its influence on the bottom portion of the grid, and the red bars would show its influence on the upper portion. So then we find the cumulative sum of these influences. So these blue dots show the cumulative sign, which will be actually the Jacobian for this particular grid cell, because it doesn't account for the influence in the lower cell, because it's the first cell in the grid. So its cumulative sign would represent this H sub 0, which will be a value of the Jacobian for this particular grid cell. This grid cell is shown here. Now the next grid cell, we take into account the cumulative sum of these red bars, and we start from here, and then we add the cumulative sum of these blue bars in the next cell. So we continue cumulative sum and arrive to the value of the Jacobian for the second cell. Again, in the third cell, we start from cumulative sign of red bars in the previous cell, and then cumulative sign of the blue bars in this cell, and so on. So this would represent the last grid cell for this Jacobian. And you see that the Jacobian value does not match with the blue cumulative sum. Instead of slightly lower. Why so? Well, it's because of the second term in this equation. It's because of the variations in the refraction height. This concept can be explained in this figure. So let's say the blue line represents the initial density in one cell and in the next cell. So let's say in the bottom cell, the density would be changed by this delta NE portion. So therefore, for a particular frequency, the refraction height would also be changed by this delta HR. Similar if at the top cell, the density would be increased, the reflection height would also decrease by this delta HR volume. Same goes that if density actually decreases, then the reflection height would increase, so vice versa. If you want to know more about the formation of the Jacobian for the virtual height retrieval, for the virtual height assimilation, you can refer to this paper, Forsyth et al. 2021b. And also another paper would describe the ionospheric vertical correlation distances, 2021a, and this paper would be helpful in the formation of this background error covariance matrix P sub f in the equation for the Kalman filter. So let's now look at some results, how this assimilative method works. For our data to generate the data, we used a very high spatial and temporal resolution radar measurements from Arecibo observatory. And we generated virtual height data points based on this known truth. So this one particular example shows the background with black line, and it shows the observed by the incoherent scatter radar data, the truth as the white line. And we generate our virtual height data points, here shown with different colors, based on this white profile. Then we assign 15% of standard deviation for all of the virtual height points, and we assign 25% of deviation for the background. Then we ingest each data point separately, producing the analysis. All of the analysis profiles are shown with different colors, depending on the ingestion of the last data point. And once we reach the last data point, that's what the final analysis will be, that is shown with the red line. This method works best when the known truth is actually the NMF2 of known truth is greater than NMF2 of the background. In case it's below, the last data point is ingested. So this last data point is ingested, and then we don't have any other data points, and the analysis will return back to the background. And in case the truth is greater than NMF2 of the background, then the profile will be extended. We also compared the sequential and simultaneous data ingestion. So what do I mean by sequential? In case of sequential, I'm ingesting each data point from lowest frequency to highest frequency, producing the analysis, then taking this analysis as the background for the next assimilative step. And in the simultaneous ingestion, we ingest all of the virtual height data points at once. So the difference in this method is so pretty high in case when the NMF2 of truth is greater than NMF2 of the background. Why? It's because of this last data points. So when the background is below the frequency of these data points, then the model data or the data that's supposed to be observed by the known background cannot be calculated. Therefore, the assimilative scheme basically ignores these last points, and the profile stops without reaching the actual height or the actual peak of the density based on observations. With the sequential data ingestion, this is not a problem. Why? Because each next profile extends the NMF2 of the previous profile, and all of the data points can be then taken into account when calculating the analysis. So that's how the root mean square errors are comparable between the analysis using sequential and simultaneous data ingestion. So the blue line shows the root mean square errors for the background, and then simultaneous is shown with yellow and sequential with red. And you see that systematically the red line is below the yellow line, meaning that the errors are reduced for the sequential assimilation scheme. That's how the truth looked like during this particular time period that we considered for our testing. That's how the background density looked like, and see how the analysis using sequential data assimilation could represent even like small variations in the electron density. This panel shows the comparison between the NMF2. Again, analysis is shown with red, and it closely follows the truth that's shown with white line. In terms of HMF2, again, you have a choice here. You can either stop by the last ingested data point, and then that will be the red solid line. Again, it follows the truth. And in case you want to rely on the background model, then the HMF2 is shown with the red dashed line. So it represents this scenario when after ingesting the last data point, the analysis goes back to the background. Or the solid red line would just stop here and consider this H and as the NMF2. We also compared our technique to the standard configuration of the POLAN inversion method and observed that our percent errors looks about twice smaller. So first panel shows the assimilative inversion, and the color represents the percent error in comparison to the known truth. And the bottom panel shows the result of POLAN inversion. You see that here at the bottom portion of the profile, POLAN shows about 20% difference between the truths, and this percent difference is much smaller for the assimilative inversion technique. So to sum everything up, this new method was developed that retrieves electron density profiles from the virtual height vertical ionosonde traces. This method employs a Kalman filter assimilative scheme with the newly developed vertical covariance model. It finds the EDP in algorithmic space by sequential assimilation of virtual height data points with the Arecibo 2016 background. We also include all the effects of the magnetic field, and all the necessary derivatives can be found in Forsyth 2021b paper. So vertical and temporal small-scale variations in the electron density were successfully retrieved by this new method, and it was found that this method works about twice better than the POLAN at the bottom side of the profile. The assimilative inversion method represents the paved way towards the routine ingestion of the vertical ionosonde traces for the large data assimilative algorithms. Thank you very much for your attention. If you have any question, please contact me. I list my emails up here on the top of the slide. Thank you for your attention.